Hi everyone. Today we'll be talking about acute stroke and how we're able to use machine learning to automatically grade a digital subtraction angiography, commonly known as a DSA scan. My name is Bennett Juwvipart, and I'm joined here with my teammates Simi, Rajpal, and Ayush Lall. So a stroke occurs when a blood vessel that carries oxygen and nutrients to the brain is either blocked by clots or bursts. Our study looks specifically at ischemic strokes where there's a deprivation of oxygen and nutrients in the brain due to a lack of blood flow and inflammation damage via neuronal death, and this affects over 6 million people in the US annually. On the right, you can see a picture of a grayscale DSA scan of a brain, and the darkened arterial and venular lines represent the blood flow that has been treated by a contrast agent. So we're able to see how the blood flows in high resolution, and because of this, it's really become the gold standard for rapid imaging of cerebral vasculature. So how we classify strokes is on a measure known as the Tiki score, which stands for Thrombolysis and Cerebral Infarction Scale. And this is measured from 0 being no perfusion to 3 being complete perfusion. And you're able to see the complete breakdown on the slide. Physicians have a really hard time being consistent on this scale, so an objective ML model would be really helpful in accurately grading different cases.
All right, let's talk about data. So at the start of the project, we were given angiographies of 201 patients, so each of which contain multiple images. So basically how the angiography works is it's done over timestamp, so you can see the blood flow. So we got something like 25 images per patient. So in effect, per patient, we had around 25 images of dimensions 1024 by 1024. So that's a lot of data. To give you an idea of how much data that is, it's around 2 times 10 to the power 10 values, somewhat around 21 GB if we assume every number takes up 4 bytes. So we had to reduce it. So we actually went two ways with this one. The first thing we did was we downsampled each of the images per patient to 256 by 256 and zero padded them depth-wise so that all patients have the same number of images. This data was then used in the 3D models. The other method we tried was pooling all the data per patient using average pooling. That is, we took the mean of all patient images to have actually of some patient images to have one 512 by 512 array for a patient. So taking the full average of all values obscured the blood vessels, so we decided to use a sample mean of the data. We took 5 images, which is like we took 5 images around the median of the time points per patient and generated a mean of those 5 images, which was treated as our features in our machine learning problem. For the labels, we had Tiki scores of 0, 1, 2, 8, 2b, and 3, which we converted into numerical values using one-hot encoding. Around 20% of the data was missing Tiki scores, so we had no choice but to drop those images.
After taking the image averages, we went on to build models. The first model we trained was a simple 2D convolutional neural net model with 6 convolutional layers. We trained this model with several different batch sizes, epochs, and variations of data augmentation, using a test set to evaluate them. Then on the best model, the model with 20 batch size, 10 epochs, 20-degree rotation augmentation, and 0.2 translational augmentation, we used stratified k-fold cross-validation with 5 folds to evaluate the model, since the data was not symmetric in the number of samples of each kind. This gave an accuracy of 45.3%. As you can see in the confusion matrix, this model classified everything into the 2B to Z score, unfortunately. We then trained an Inception v3 model, one of Google's pre-trained models with ImageNet weights. We also modulated similar parameters and found the best model, with a batch size of 30, 10 epochs, 90-degree rotation augmentation, and 0.5 translation augmentation. After 5-fold cross-validation, we found that this had an accuracy of 46.5% and was more successful into categorizing. One important thing to note is that 77% of the data has a TISI score of 2A and 2B, and about 43% has a TISI score of 2B. This left the model with little ability to understand the score of 0, 1, and 3.
Alright, so the 3D modeling we did, in that original idea was to treat the data as 3D objects, with time being third depthwise axis. However, proper 3D convolution was not exactly appropriate, as the data isn't truly 3D. So to get around this problem, we used depthwise convolution and multi-view convolutional neural networks. So depthwise convolution is a carousel layer that treats a dimension as the depth and thus does convolution as a stack of images. We tried a model with 6 layers of depthwise convolution with kernel sizes increasing after every 2 layers and a max pooling layer after every 2 layers, mimicking the ResNet models. So this gave us a test accuracy of around 41% at best, so not ideal, so worse than the k-fold cross-validation stuff we did. The other concept we tried was multi-view CNN, which, as shown by the image on the side, runs each image in the stack of images through a separate convolution and then pulls the image together. However, this was also not a major improvement to results from depthwise CNN, so we decided to not move forward with this concept.
So the best model ended up being the Inception V3 model, as mentioned before. This model had a 46.5% accuracy and can certainly be improved. More image processing techniques can help us improve this model. So we can regularize the time domain to allow us to know exactly where the different perfusion phases are to improve our averaging techniques or to improve the 3D convolutional model. We can find ways to crop the images to only the significant information. This was difficult because of the rotations and shifts in some of the images. We can also try using difference gradients to allow our model to see a clearer view of the blood vessels. We can even improve the complexity of our models. If these problems are solved, this will have a great impact on numerous medical radiology problems.